Hi, I'm going to explain the problem strange number from April Challenge 2020, and it's kind of a really interesting problem. It requires the basic knowledge of factorization and prime numbers, so it's interesting. And the problem is there is Vasha, and he wants to know if exists some number A such that this number A it has exactly X divisors, and also she wants that given these X divisors, she wants that K of them are prime. So she wants to know, she only wants to know, she doesn't want a number uh, that has exactly X divisors and exactly K of these X divisors are prime numbers. So this is the problem, and it's interesting. In first moment, a solution where we test all the possible numbers and keep testing seems an interesting solution, but it's going to time out because then A can be pretty large, so it's not a solution. And the first thing that we should note here in this problem is how to calculate efficient the number of divisors of a number. And there is a good way to do that, and this is like, let's suppose we have this number A, and A can be represented as a product of primes elevated to some power. To be more exact, it's like we have a prime 1 here elevated to exponent 1 here, and the same thing to another prime 2 elevated to a 2, and we keep going like this until a prime n elevated to some power n. And any number can be represented in this way. Is basically how you factorize this, but we are grouping the prime numbers that are equal. So each prime number here is different. And to calculate how many divisors this number has, we can calculate it as a product based only on the exponents. We don't have to the numerators to be taken in consideration, the base to be taken in consideration. So the number of divisors can be seen as a1 plus 1 multiplied by a2 plus 1, and we keep it going the same way until an plus 1. And this is interesting because now we kind of have some way to know x, because if this equals to the number of divisors, we know that we want this to be equal to x. We want this equality to be true because it's what is mainly how the number of divisors will be calculated. So we already have one thing in the problem, that's how to calculate the divisors, but the main thing is we need k primes, exactly k primes. So in this point, we have divided the number a in some primes here, and we want that when a is represented in this format, we want this n to be equal to k. And this is interesting because let's look at factorization of x. The factorization of x can be seen as this. The factorization can be seen as the product of many numbers, and then we can kind of know how much primes we can afford based on that. To be more clear, let's make some examples. Let's say 12. What is the factorization of 12? It's not in this format, is the more extensive formula. So we go to 2 times 2 times 3. So this is the factorization of 12. It's 2 times 2 times 3. And we can kind of go in matching this 2 to the first one, this 2 to the second one, and the third to the third one. And we now have a way to create a number a such that this number a has exactly 12 divisors because we can put any prime number here for going to be the base of 2 because it doesn't matter the prime number. It only matters that they are different, and then we can put any prime number here. But let's keep thinking about it. So, if the factorization of our x has less than k primes, then it's already possible. Let's think about it, because let's say we want exactly 12 divisors and k of them is going to be primes. And this k is going to be 4. And so we are doing some example like x equals 12, k equals 4. We have factorized the number and we want this structure to A to have 4 prime numbers as the base, but we can't factorize more the x. We can create another exponent to this number because, for example, all the numbers here are already prime, so we can't divide prime number in another prime number multiplied because it's a prime number is only divisible by 1 itself. So if the factorization of x has less prime numbers than k, it's already possible because we can assign some base to the last number. And this is kind of one important thing in the problem. So factors of x is equal to the number of factors in factorization. So we can see now that if factor of x is less than k, then we can imply that the answer is no. There is no number a that can suit this problem. Now, if we think about, in this case, if we're looking for k equals 3, then we can do it because we just have to assign the prime numbers and we already have the exponents. The exponents are the factorization numbers minus 1 because in this formula it's like they are plus 1, so we have to put minus 1. An example would be, let's do this example for 12 divisor and k prime. We can put the number, let's say the first prime is going to be 2, the second is going to be 3, and the last one is going to be 5. Then the first exponent is going to be 2, but we have to do minus 1, so it's 2 to that 1, and the second is the same thing, and the 5 is going to be to the square. So if we take this number is, so this is equal to 150, and if we look at 150, you're gonna see they have exactly k prime numbers, and it has exactly 12 divisors that we require here. So it has 3 prime numbers here and 12 divisors. So 150 is good, but we don't have to calculate the number. We just have to say yes or no. So we know now that if factors of x equals to k, then the answer is yes. So there is only one case missing here, that is factors of x bigger than k. And we can think about it for a moment. Let's do the same thing, 12 divided by k equals 2. And we can build it because we can merge some numbers to make a new exponent. For example, instead of having all of the factors of 12 as exponents, let's say the exponents are e1 equals 2 and e2 equals 6. So this is also equals to 12, so we are fine here. And we can assign 2 and 3, the same prime numbers before, but the exponent will be 1 and it will be 5 here. And this is equals to 486, and it matches our necessity. So this is going to be equal to dx also. So the answer only depends on this function factors. If we can calculate the number of factors in a number, then we can solve the problem. And to do that, we can simply use the square root factorization of the number. It's not that hard, it's just a bit simple, but it's enough for this problem. For example, if we want to factorize the number n, we can go until the square root of n, removing the primes, and then we're gonna have the factorization, and we can count how many primes there is, and this will run O of square root of n for the number n. So with that, we can factorize the number, and this is enough for the whole problem during the factorization, because we don't have we don't require a faster implementation of factorization. We just require auto thinking in how to solve the problem, how to calculate the number of divisors, how to see if k prime is enough or is not enough. And that's it for this problem. I hope you enjoyed watching, and bye.